Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will work on an example for a continuous uniform distribution. This example will help us revisit a couple of important concepts in probability theory. The concepts of probability density function and cumulative distribution function. It will also give us a great excuse to play around a little bit with R. Well, let's begin. That's the example I would like to work on with you. Okay? So, in this case, the random variable y represents depth. Well, the change in depth of a river. Okay. The probability density function for that random variable y is given by a constant, but that constant is unknown, and that constant is defined over a finite interval, the interval -2 to 2. So first, what we would like to do is finding the value of k that makes this expression a formula for a legit probability density function. And next, we would like to obtain the CDF, the cumulative distribution function for y. Okay, so first, to find that value of k, we have to recall what are the two properties that a legit PDF must satisfy in order to be that, a legit PDF. So, first condition, the PDF must be non-negative. So it could be 0 or positive, right? So now we know that k must be a positive number. Okay? Second condition. The second condition that a legit PDF must satisfy is that in this case we have a continuous random variable, right? So in this case, the second condition is that the integral from -infinity to infinity of the PDF must be equal to 1. Okay, so let's use that second condition to find that unknown constant k. So we know that, again, let me rewrite that second condition that we know, f of y, the PDF must satisfy. The integral from -infinity to infinity of f of y must be equal to 1. So in this case, right, that would be equivalent to the following three integrals. The integral from -infinity to -2 of 0 dy plus the integral from -2 to 2 of k dy plus the integral from 2 to infinity of 0 dy, right? Because we know that the PDF, right, will be k only between -2 and 2, and it's going to be 0 elsewhere. Okay, so it turns out that the only part that matters is the integral in the middle. Okay, so let's get rid of the first integral. Okay, let me just copy paste this one. Let me get rid of that one. That one. Okay, there we are. So that's the only one that matters. So now let's use the linearity of integrals. Okay, so this is the same as k times that integral from -2 to 2 of dy. That's an easy integral. That's just going to be k times y, and y will be evaluated at 2 and -2. Okay, so this is the same as 2 minus 2, and that is going to be equal to 4. That's the same as k, well, 4 times k equals 1. So in the end, k is going to be equal to 1/4, or 0.25. Okay, so now we have that constant k that makes our PDF a legit probability distribution. Okay, part B. We want to find the CDF. Okay, so the first thing that we have to do is remembering how CDFs are defined, right? So recall that we use first an uppercase F to refer to the CDF of a random variable y evaluated at a particular value, lowercase y. And by definition, right, the CDF of a random variable y is given by the probability that the random variable y is less than or equal to some number. Okay, that's the CDF, uppercase F, evaluated at y. Okay, now in this case we have a continuous random variable. Okay, so to find that probability, again, we're going to need an integral. But just like this guy, the PDF is defined for any number over the real line between -infinity and infinity, right? The CDFs must also be defined over the entire real line. So let's find the CDF for all the possible cases. Just like this integral, right, could be broken down into 3 different parts, we're going to have 3 cases to define the CDF. Okay, so first, if y, lowercase y, if you're evaluating the CDF at a number that lives between -infinity and -2, we're going to have one case. Okay, so case 1, if y is less than or equal to -2. Okay, so let me borrow this, the definition. So if we are evaluating the CDF at a number lowercase y that is less than or equal to -2, clearly the probability is going to be 0, right? Because we would be taking the integral, you know, the area underneath the 0 constant, right? So 0, okay? Okay, so case number 2. Now let's think about the y's that are between -2 without including -2 and less than or equal to 2. Okay, again we use the definition. In that case what we have is the integral from -infinity to -2 of 0 dy plus the integral from -2 to y of, now we have that constant, it's 1/4, right? 1/4. You have to change variables here, so let me use t, dt, right? Makes sense? Okay, so now the only one that matters here is this guy, the second integral. Just like before, let me use the linearity of integrals. And this is just going to be 1/4 times t, right? That would be the integral. We have to evaluate at y and -2. So I'm running out of room, so let me continue here on the next line. So this is going to be the same as 1/4 times y minus -2, right? So this is going to be just going to be y divided by 4, right? So let me write it down like this: y divided by 4 plus 2 divided by 4, which is just 1/2. Make sense? Okay. So we are done with that part, with that case. Let's talk about the third case, just like we had here, right? When y is between 2 and infinity, right? If we have that case, if y is greater than 2, right? We use the same definition as before. But again, if we did that, right, it would be the integral from -infinity up to that number y that is greater than 2, right? But if we go beyond that, then, you know, for instance, say that y was 3. Clearly, right, the probability that that random variable is less than or equal to 3 is going to be 1, because we have taken into account all possible non-zero values, right? So 1. Make sense? Okay. So, we have done parts A and B entirely by hand, right? This will be important to remember how to do these things by hand, and I'm going to be showing you how to do it both ways, by hand and with R, because remember that our final exam will be in person, so it will be a regular in-class final exam, so it will be important for you to know how to do things by hand without the aid of a computer. Okay, but I'm going to also show you how to do this using R. Okay, so let's redo this using R. So first, part A, right? Let's try and show that the constant that we obtained, 1/4, it's okay. It's 1/4. Okay. So first, I am assuming that you have already downloaded and installed R in your computer. Okay. So let's launch R. So first, for part A, and remember that if you want to make a comment to your R code, all you have to do is type a hashtag, and then whatever you type after that hashtag is going to be ignored by R. So it's just a comment. So I'm just saying that we're redoing part A, right? We're finding K again. Finding K. Okay. So now the next part I don't want R to ignore. Okay, so this was just a line of code and then a semicolon, and then I'm done with my comment there. Now the next R command, R will take into account. I want R to help us find that constant. Okay, so let me define our function. So note that let me go back to what we did by hand. I will try and find just this part. When we factored out that K, let me find this integral, the integral from -2 to 2 dy. Okay, so if I find this guy, then K will be just the reciprocal of that integral. Okay, so again, I'm going to be finding the integral from -2 to 2 of dy using R. So let me define a function, and you can use the arrow, well, an arrow or an equals sign to make an assignment here in R. So let me use the arrow option. So function y. Okay, so I could try and write just 1, right? That's a function that I would like to have here, but I'm going to be very specific with R. That is the same as y. A 1 is the same as y to the 0 power. Okay, let me show you why I'll do that. Let's try and just use a1 and see what happens. Okay, so the function that I'm trying to use is this function integrate. I want to integrate function f from the lower limit for that integral is -2, right? And then the upper limit is 2. And guess what? It doesn't work. And then you go, hey, R, that's a simple integral. It's just the integral of a constant. How come you can't deal with that, right? So the thing is, we need a variable here, y, and y to the 0 power is the same as 1, right? Now, if we integrate that same function from -2 to 2, if everything goes well, guess what? That's 4. And now what we did by hand makes sense. If that integral is 4, we have 4 times k, and then k is the reciprocal of 4, which is 1 over 4, which is what we got doing things by hand. Okay, so using this function, you can integrate using R, you can integrate functions with this. That built-in function integrate, but what you have to do first is define that function. Okay, so part A done. Now let's try and do part B. Let's try and make a graph of our CDF. Okay, it would be nice to see that CDF. What we have here is this: k is 1. For y's that are less than or equal to -2, we have 0. That's a CDF. And then if y's live between -2 and 2, we are going to have y divided by 4 plus 1/2. So that's a line with a slope of 1/4 and a y-intercept of 1/2 between these guys, -2 and 2. And finally, if y is greater than 2, then we're going to have just 1. Okay? Well, let's try and make a graph of our CDF using R. Okay? So first, let me create a sequence of numbers. So here, let me see what happens if we do something like this. A sequence of numbers, the syntax of this function is first you have a starting point, an ending point, and then the distance between the numbers that form your sequence. So say that we had just something like this, right? That I created a sequence of numbers going from -3 to 3, and the distance between each of the members of the sequence is 0.1. Okay, so we have this, right? Okay, now that you have seen how that works, I'm going to be using the same function, but I want to have more elements in it. Okay, and I'm going to be saving that sequence in an object called X. And instead of using the arrow, just for fun, I'm going to change it a little bit. I'm going to be using just equals. Okay? Okay. Okay. So, now, we know, now that we see the expression here, we go, oh yeah, so you have between -2 and 2, you have the expression is 1/4. That is clearly an example of a continuous uniform distribution. So R has that function, a continuous uniform, right? So let me just show you something. I know the name of the function that helps you evaluate the PDF of a uniform. It's the UNIF. So if you want to know more about that function and you already know the name of the function you want to use, just type help, the name of the function, in this case, uniform distribution, the UNIF, PUNIF, and so on. You have different options, right? So in this case, the UNIF gives you the density. Okay? See? That's going to give you the density function. Okay? So first, I'm going to make a graph of our density function. We already know what it looks like, but just, to play around with R. Okay? So the syntax of that function is, first, I want the density of a uniform evaluated at some point, and then the arguments that I need is the minimum and the maximum. Okay, so here we go. Let me call that guy fx. and then it's going to be the unif of x, right? The sequence of numbers that we created here. The minimum in this case is -2, and the maximum is 2. Okay. Now I want to make a graph, right? So I'm going to be using base R, right? So the syntax to make a scatter plot goes like this. First, the numbers that go on your horizontal axis, and then the names that the name of the variable that goes on your vertical axis. Okay. Okay. So and now I'm going to be using an additional argument, pch equals 19, and that's just to tell R that what I want is solid circles. Okay, that's the the character that I want to use for my graph. Okay, okay, so we already knew that, right? That between -2 and 2 we would have just a horizontal line at 1/4. So that's a basic graph of our PDF, of our probability density function. If you wanted to make it look slightly nicer, you could do something like this. X lab as in the label for the x-axis. Since here what we had is y, let's use that. Y. The label for the vertical axis, the y-axis, f of y. Okay. Then there you are. Y, f of y. Okay. Okay. And you could also add a main title with something like this, right? PDF of y. So just with that additional argument, main, that should work, right? Okay. So we have a graph of our PDF. Now let's try and find the CDF. That's the one we want. Okay, so it turns out that just like the unif gives you the density, the function punif gives you the cumulative distribution function. So let me create an object uppercase fx punif, and again that is just the built-in function, the special command in R to get the CDF for a uniform. Okay, so we want to evaluate at those numbers x. The minimum is going to be -2, the maximum is going to be 2. Okay, and now again we're going to recycle what we did before. We have a plot, right? We want x on our horizontal. We want now uppercase f of x, the CDF, right? And again I want solid circles. Label, I'm going to be using y as we originally had here. Now it's uppercase f because it's the CDF, and now I'm going to be saying that what we have there is a graphical representation of the CDF, the cumulative distribution function. Okay, so all right, makes sense. So we have 0 for numbers that are less than or equal to -2. Since we created a sequence between -3 and 3, that's what we're seeing. Between -2 and 2 we have a line. It's supposed to be a line with a slope of 1/4 and y-intercept 1/2, and it seems to be there, right? Makes sense? Okay, so we're done here. Let's summarize what we did here. We talked about a random variable that you have seen, that you have dealt with before, a continuous uniform random variable. We talked about the properties of PDFs, right? In particular, that a legit PDF, a continuous one, right, must satisfy the following condition: that the integral between negative infinity to infinity of the PDF must be equal to 1. We used that to find the missing constant, right, for a uniform, a continuous uniform, and then we found the CDF, right? And at the end, just as an extra, we started playing with R, right? So now we know how to create sequences with R, and we know how to make basic plots using R. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.